Hello and welcome to part 2 of lecture 18. Here we're going to continue to talk about chapter 24, and that is wave optics or physical optics. And this time the topic is something called a diffraction grating. So let's go ahead and define what a diffraction grating is. I think it has a good functional definition, one that we can work with nicely. All right. So it is simply an array of mini slits. Okay, because we talked about the double slit and the single slit, right? Both of which creates interference patterns. Well, what if you have 3 slits? Well, I mean, that's kind of a story for a different day. But if you have a lot of them, then it's called a grating, okay? So it's an array of mini slits. Slits are just openings, okay? Usually hundreds or thousands. Maybe not hundreds of thousands, but hundreds or thousands. Hundreds or thousands. All right. It has uses for science to carry out spectroscopy, which is the identification of particular colors. So used in scientific spectroscopy. Okay, so not too much there to the definition. I think it's a pretty straightforward idea. All right, the openings are still going to be small, the slits. That's implied by the name. So they're going to be on the kind of spacing that's similar to the wavelength of light. In fact, the spacing is going to be closer to the wavelength of the light that it's being used for than a double slit. Okay, and let's go ahead and use that as a segue to identify our one key formula here, which is simply this right here. Okay, so I'll say what it is, and then I'll say why it probably looks so familiar, and then why we have to use this particular form. Okay, so simply this formula tells us the location of maxima. Okay, it's the angular location of maxima. So this is the angle of interference maxima. Because of course it is the interference, right? Superposition of waves that creates any sort of maxima or minima, or anything in between. Interference maxima. Okay. D is the slit spacing, so distance between slits. Okay. In this case, it would be the distance between any 2 slits, because that is an assumption that we make all the slits are evenly spaced. Okay, kind of makes sense. It'd be quite odd to have a bunch of them really close together and some big gaps, right? They'd be very different. M is just the order of the maxima. Okay, so the order of maxima. All right, so if we have, if we think about the location of finding, the central maxima, right? That central bright spot. That would be an M of 1. Okay, that would give us the angle that corresponded to the central that central location. I believe. Let me double check that. Yeah, certainly we have. Yeah, because just like before, we had we're always counting up from 1. Just trying to think about what kind of the main consequence of that is in terms of thinking about double slits, perhaps. So here, let's take a quick detour. Open up lecture 17. All right, if you'll indulge me here. All right, so if we go back to when we first introduced our constructive interference locations, right? Because that was, in other words, interference maximas right there. Okay. When we did that for the double slit, we had the same exact formula, right? Which is the thing I was going to mention. I'm sure some of you realized, right? That the formula that you're just looking at a minute ago for the diffraction grating was literally the same thing. It was d sine theta equals m lambda. Okay. So it's almost like the diffraction grating is just acting like a double slit. What's the difference? Okay. Well, I'll speak to that. There's not a big difference, but there's something you want to pay attention to. This one, so one little thing you need to remember. Okay. And then, so if we think of the locations of that central bright spot, having so with an m of 1, then we should have our central bright spot, right? That should be the location where we have yep. Okay. So I see here. Okay. Yeah. Yep. So I guess I wanted to go back and clarify this, because I think that, so here I clearly spoke to it being m of 0, and that's right, because the central one has to be m of 0 because the path length difference is 0. So the central bright spot for a double slit, and incidentally, something I'll get back to, for the diffraction grating, the central bright spot corresponds to an m value of 0. And so really, the values for m can be 0, 1, 2, 3, and so on. Okay? So it does make sense to have an m of 0. And I think the reason I'm clarifying that so much right now is because I believe in the previous video I said, oh, well, look, when we were looking at the single slit interference, I'm like, look, it's only m of 1, unlike for thin film interference where you can have an m of 0. And I was like, oh, I think thin film interference is the only time where you can have an m of 0. Well, that was wrong. That was me misspeaking, because you absolutely can have an m of 0 for the double slit. In fact, going back to lecture 18, if we look at the single slit, we can think of it as the exception, because this is the case where m can only be 1 or greater, right? 1, 2, 3, 4, right? It's an integer excluding 0. And so because there is no 0th order minima, right? The first minima, right? I'm just highlighting over here if you notice, right? So the first minima is that one. Well, that's an m of 1 in terms of minima. There's no such thing as central one, so there's no 0 one. Now there would be a central bright spot, path length difference of 0, but when we talk about single slit interference, because of the approximations involved, we actually don't identify the locations of the bright spots in general. We always only identify the dark spots, and kind of hand wavy say, oh, well, halfway in between the bright spots. But see previous video for that. But anyway, to not get too much off topic, the important thing, the clarification, is that we can have an m of 0. And so then if we go to our current topic, the m can be, so that the order of that bright spot can be anything from 0 to whatever, right? So it's 0, 1, 2, 3, etc. Okay? With 0 being the special case of the central one. Okay? Lambda is just the wavelength of the light. So, as we saw, right, this formula isn't new. This is literally just the formula for location of bright spots for the double slit. Then why even have a special case of diffraction grating? Because of this. Because this formula, this one right here, is the only one that we can use for diffraction gratings. In other words, the only thing you really need to remember, I'd say, is that you have to remember you cannot use the small angle approximation for diffraction gratings, which means you can't use any versions of locations of whatever on the screen, okay, some distance r away or whatever it may be. You can't ever use any formulas that don't have a trig function in them if you're talking about diffraction grating, right? So like don't use it and then forget, right? Remember that every time it's diffraction grating, you have to use the one that has the trig function in it. Let's make a note here. Small angle approximations can never be used with diffraction gratings. Okay, so two slits, yeah, it works a lot of the time. Now, why is that, right? Well, really, it's just a rule of thumb. It really is. It's a practicality, because diffraction gratings tend to have a very small value of d. When you divide by a very small number, you get a big number, and so that means the sine of theta is actually going to be a relatively large number, and so that means that theta is not a small angle. It's as simple as that. Okay. Whereas when you have a typical double slit, like you use in a laboratory for a kind of learning lab, well, the spacing can be some fraction of a millimeter, maybe it's a tenth of a millimeter. Well, that's actually a pretty large spacing compared to the wavelength of visible light. So there you go. That is a small angle, okay? Especially if you have a screen a few meters away. But in the case of diffraction gratings, it doesn't matter if your screen is 10 meters away, 30 feet away, right? Because you're actually still going to have a large angle, all right? So could you perhaps have a diffraction grating? The screen is so far away or something, or maybe the grating is so big that that, D is not that small, yeah, but then it's kind of not even a diffraction grading. But again, it's a rule of thumb, okay? But point being, it was always an option to use a small angle approximation. We never needed it per se. So here we just shouldn't use it. All right, I think I've said enough on that. Let's take a look at an example. Okay, so we got example 1. If a diffraction grating produces a third order bright band at an angle of 78.4, right? Angles, not distances. Okay. For light of wavelength 652 nanometers, excuse me. Find the number of slits per centimeter for the grating. And, well, we'll go from there. Let's find the number of slits. Okay. So, part A of example 1. I'm going to show you 2 examples, by the way. This one and one more. So, what do we know, right? Well, we know the formula we're going to use. D sine theta, and that's going to equal m lambda, okay? We're looking for the third order, so that's going to be an m of 1, okay? And so then we want to find the D spacing. So let's go ahead and solve for D. Okay, so that means that D is going to equal 3, because m of 3, times the wavelength of 652 times 10 to the negative 9 meters. And then we'll simply divide by sine of 78.4 degrees. Okay, so that gives me a spacing of 2 millionths of a meter, 2 microns. Okay, so that is a very small spacing. Okay, but again, that's more typical for diffraction gratings than for just double slit. Okay, then I was asked, however, how many slits are there per centimeter? Well, that's simply a matter of saying like, okay, well, if there's that many slits per meter, if that's the distance, then I can find slits per meter, or I can find slits per centimeter, right? So if I simply take 1 over D, that's slits per meter, and then if I multiply it by, or divide it by 100, then that'll be slits per centimeter. Okay, so we'll say thus 1 over D times 100, or excuse me, divided by 100, times 1 over 100 gives, well, be 2 times 10 to the negative 6 meters, okay? And then to the negative 1 power, so that's going to be 1 over meters, something per meter. And then the 100 part is simply the number of centimeters per meter, okay? Or meters per centimeter, excuse me. So meters per centimeter, okay? And you can see when I do that, then I'm going to get the right units of just something per centimeter. And what will it be? Well, it's just 5,000. Okay, you can plug that in your calculator. But it ends up being 5,000, and it'll just be per centimeter, which would be the same as just writing centimeter to the negative 1 power. Just like a frequency is per time, and you write seconds to the negative 1. Excuse me. Okay. All right, now part B. Okay, so this one we're asked for the angular location of the first order and second order, okay? So we should be able to find those relatively easy, okay? So if we wanted to find theta, first order and second order, so we'll find the second one first. All right, so that's just going to be sine inverse of m lambda over d. Okay, so in this case, it's going to be 2 times 652 times 10 to the negative 9 meters, all over d, which we now know to be 2 times 10 to the 6, negative 6, excuse me. All right, units cancel out there as they should, and the meters. And so that, for the 2 case, that gives me 40.8. Okay, and then let's find the first order bright spot. Okay, so the same thing, theta 1. All right, this one I'm going to go ahead. I won't rewrite it, it's in the exact same form. I just have a 1 instead of a 2, right? That's the only difference. And so if I did that, if I did sine inverse, got to recalculate this one. 652 times 10 to the negative 9 divided by 2 times 10 to the 6. All right, so 19. Nice. And of course, the 0th order bright spot would be an angle of 0, because it's right in the middle. And it's 19.0. degrees. All right, so there's our two lower order ones. So these are pretty spread out, right? If you think about it, right? I mean, these angles mean that like these spots are inning up pretty far. You know, you think 78 degrees. I mean, that's really on the edge of the screen. You know, that's like quite an angle. And you got to think. I mean, like, well, how big is your screen to even capture that? You know, if like I'm standing in a room, I'm looking at a wall, and I draw angles to the corners of the room, a lot of times those angles aren't going to be 78 degrees, right? I'd have to have very long room to be able to even capture that type of angle, okay? Well, here's the thing, but of course there's a limit that a room can only be so long and capture a certain angle, right? You can never capture an angle above 90 degrees because, you know, it wouldn't be a screen anymore. You'd have to have sidewalls to capture that, okay? And that leaves us part 3. Will there be a fourth order bright band, okay? Well, no, right? Because anything greater than 90 degrees is going to be, it doesn't actually show up on a screen. So I'll say, first let's find it, right? So theta 4 would just be sine inverse 4 times 652 times 10 to the negative 9 meters all over 2 times 10 to the negative 6, okay? Now we could have asked this kind of question with the just double slit, but it probably would have been the 14th order, right? So it'd be a much higher number. Yep. And let's see, so then the angle I actually get in that case is, well, it's undefined, right? Because it's not, simply it's not going to show up, right? Go ahead and try it in your calculator. If you do sine inverse, and you take 4 times 652 times 10 to the negative 9, divide it by 2 times 10 to the negative 6. All right, it's undefined, okay? So, well, that tells us that no, there is no fourth order, okay? It doesn't, you can't have a path. There's no way to get to that path. There's no way to achieve that path difference, okay? And again, that's because we're assuming a triangle here. So we're assuming a wall. Could you have a path difference that's going to be on, you know, to the side? Yeah, but that'd be different geometry, okay? So in this case, right, the triangle that we're looking at, a screen, it doesn't work, it doesn't exist. So there is no fourth order bright spot, okay? Okay, so hopefully that makes sense. Let's take a look at one other example. Example 2 and 3 are straightforward. I leave them for practice. Okay, it's good to just make sure you can work out how to do these types of problems. Okay, more in the study guide as well. But let's look at example 4. A diffraction grating is built for astronomical measurements of the 21 centimeter line, microwave indicative of atomic hydrogen and created by the hyperfine splitting caused by the electron spin states. Kind of a neat idea. That's, you know, something we'll talk about briefly in one of our last chapters. But here, we just want to use it as a real life application. Question is, how many slits will this grating need if the goal is to distinguish between the 21 centimeter and the 21.001 centimeter on the second order maxima? And that's the thing, because, you know, it is hyperfine splitting. And so we would have to have that sort of a resolution. Notice here that the light is measured in centimeters. That's because we're talking about microwaves. Microwaves, like the light they use to cook your food, it is light, invisible light, right? And much lower energy than visible light because it has longer wavelengths, and its wavelength is generally on the order of a centimeter. Okay, and these particular microwaves are right on the edge of their long microwaves, and then if you get any longer than about 30 centimeters, then you're not really a microwave anymore. You're just a typical radio wave. Radio waves are going to be, you know, many tens of centimeters or many meters long. Okay, even kilometers. All right, so that means we need a certain amount of kind of resolution here, right? We need to distinguish, and then let me finish here. So it says on the second order maxima with an angular separation of 0.01 degrees. Okay, so we need that difference, right? So in other words, we need to make sure that the second maxima have that much angular separation. Okay, so how do we set this up? Well, let's start the formula. We know we're going to use this. So we're going to use d. I recently rewrote this to not use the material we're not covering. So let me work through it with you all. And so then there's going to be m lambda, okay? And so the idea is that we need the difference in theta. So if we could find the two results, okay, so if you think about it, then we're going to have theta and we'll have theta, this will be theta for 21.000 centimeters, and then theta prime for 21.001 centimeters. Okay, those are going to be our two different angles. And we need to make sure that that angular difference is less than 0.01 degrees. Okay, so, and we want delta theta. I'm going to set it equal to, right, because it'd be less than or equal to. And then that's this going to be, which one is going to be the bigger one? Let's see, it's going to be the theta prime. Okay, so minus theta is going to be less than or equal to 0.01 degrees. Okay, and we'll just use the equal to part. Okay, so then we just need to find the d that makes that happen. Okay, so then let's see what that looks like in the next equation. So then if I'm thinking of solving each of these, so theta prime would be sine inverse of d, m lambda over 2. Okay. Okay, and that's going to be the, that will be lambda prime, because that's the 21.001. That's the slightly longer one. Okay, and then I'll subtract sine inverse of m lambda. That's the true 21 centimeter line. And then we'll also be dividing that one. I wrote d, but I meant 2. I was just thinking m equals 2. That's why I wrote the wrong thing. And now we're going to set that equal to 0.01 degrees. Okay, so make sure we want this in degrees. You're okay. So then with that, we know we're going to want to solve for d. M is just going to be equal to 2. We got lambda's all known. So the way we want to do this, right, because we need, just thinking about kind of setting this up. Because we got our two inverse sine functions. I could just take, so those are just numbers. Is there, I'm trying to think about a property that will allow me to sort of, to combine them, right? Or do I want to set this up slightly differently? Because ultimately, you know, that the setup's fine. I'm just thinking about the algebraic solution here. So I took, you know, obviously taking sine of a sine inverse, right? If it's just a single angle, then I could just, you know, just take sine of 0.01, right? That's going to be my angle here. But I'll have a difference between the angles. Yeah, what are the properties of inverse trig functions? Let's think about this. So I'm just going to do a quick search here. Again, it's, you know, kind of a change here that I made to the problem, and hopefully I didn't make it unsolvable. I don't think I did. So inverse trig functions, and I want identities. You know, I'm thinking like a sort of like a difference between angles, but of course here it's a difference between, you know, it's just the two angles. Okay, so yeah, we obviously have, yeah, so you know, sine of sine inverse just gives me the thing inside. Okay, and that'd be fine if there wasn't a difference between them. But what to do when I do have a difference between them? Right, when I'm two different arcsine functions or sine functions. Interesting. So, so we got a certain angular separation, a certain resolution. Um, That's fine. I took the two functions and solved for their angle. Could I do this without setting it up as a single equation like this? Could I say, okay, well, I got the one, just find what the angle is, find the other angle, and then, but then that would just be trial and error, right? Because it'd be like, oh, okay, well, in this case, they're this far apart, and then, yeah. And I also probably should have specified how many slits, like per something, how many slits per meter. Let's say how many slits will this grating need. Unless I gave it the size of it. Interesting. So I just don't think I could get away with just saying that those two, kind of those two functions that I couldn't just take sine inverse of both sides, or just take sine of both sides and say, oh, well, that's just going to give you the difference inside of it, right? It's not, I don't think I can distribute it. I also don't think that sine inverse of those two angles would be the same as sine inverse of one minus the other. Would it? No. Well, yes. Because I'm finding one angle, and let's say it's 45 degrees, right? And then if I took, so let's see if this works. I'm going to go on a limb here. So I'm going to say that this is the same thing. Okay, so then I have m lambda prime over d minus m lambda over d. And then that's just an equal 0.01 degrees. Okay, and then I'm just going to go ahead and then take sine of both sides, okay, which will again get rid of the sine inverse. Then it's just a matter of finding the d, okay, so let's do that. So then that would look like this. So then I'm going to have, well, I obviously would want to cross multiply by m, and let's make these 2's. Okay, because I know that m is equal to 2. Okay, make a little note of that up here. So m equals 2. Good. Okay. So anyway, so then I would have sine, move the left-hand side to the right-hand side, or right-hand side to the left-hand side. I'd have sine of 0.01 degrees, okay, multiplied by d, so just cross-multiplied. And then that's going to be equal to the difference, so that's going to be 2 times lambda minus lambda, or lambda naught minus lambda, okay. And I'm pretty sure this is going to work. I'm pretty sure I can just, because it's ultimately just a difference between angles, okay? And the difference between angles is exactly that. So yeah, I have to confirm that somehow, but maybe it's just intuitive. And so anyway, so I want to solve for d. This will be my slit spacing. Then my d is going to be 2 times 21.001 centimeters minus 21.000 centimeters. Right, so we know what that's going to give us. And then just divided by sine of 0.01 degrees. Okay, so like that. 0.01 degrees. Okay. Okay, so that's going to give us our spacing. And then 2, so times 21.01 minus 21. Okay, and then divided by sine of 0.01 degrees. Okay, so that gives me 11.45. All right, so that's the spacing between the slits. Okay. Um, wow. Oh, because I left those in meters. And I'm like, wait, that can't be right. It's not going to be that many meters, right? Okay, so this would be 0. Here, I'll just do it like this. So I'll have 21.001 minus 21, close parentheses, and then multiply that by times 10 to the negative 2 to get it in meters. Okay, because I can't leave it in centimeters. Okay. All right, so let's go ahead and do that. Okay, so then I have a spacing between my slits of 11 centimeters. Okay, so half the wavelength. Okay, you might be like, but 11 centimeters is really big. Well, yeah, but our waves are really big here too. You know, if this would be like finding a slit spacing that was 500 nanometers for some visible light experiment, that'd be a crazy, crazy tight slit spacing. It's just that here we're talking about much larger waves. And so then thus, the number of slits, how many slits, is just going to be the reciprocal. So d inverse is, if I just raise that to the negative 1 power, or the reciprocal, I guess, then I end up with 8.73 slits per meter. Right? So sorry for the meandering path there, but hopefully the final result is worth it. Okay, so that's going to go ahead and conclude the second part of Lecture 18. There'll be a third part where we talk